We are live.
All right. You want to introduce the prompt, Mayor?
Sure. And there's a lot of talk now about robots. Suddenly it's, waking up again. And a traditional robot is either one of those clunking humanoid robots that looks like a transformer, or a robotic arm that's inside a factory and screws things together or paints cars and stuff like that. But the robots that we're actually seeing, have a different range. So we have wheeled robots doing deliveries. Yes, we do have humanoid robots, but we also have drones, some of them autonomous. And trying to figure out what makes something a robot and not just a machine. And I know I've mentioned before a friend of mine who said that his robotics professor used to say that if you have a problem and your solution is a robot, then you're a bad engineer. So that's maybe an exaggeration, but there's something about a robot which means that it's has many degrees of freedom and it works under less constrained conditions. And the first question is, so what do we consider to be a robot? An autonomous car, is that a robot? I don't know. And especially since you have different levels of autonomy. But once we get past that, it's interesting to consider the revolution happening before us of AI powered robots. And, where is the AI in these robots and why is it different? Other than saying I have a electrically powered robot or hydraulically powered robot, I have AI powered robot. So that's the subject. What makes a robot from I don't know, cultural perspective?
So the session I'm remembering from, or two sessions at least that I know I was in when we touched on this. One was really long ago, and we brought up this. I think I forget where it was, but yeah, I had some slides somewhere on a spectrum from exploration to terraforming. So if you look at an environment like Mars, on the one extreme, exploration means the entire environment is completely wild, and it's one way to like restate wild is it has no usable intelligence affordances. So it might have other kinds of intelligence, including hostile intelligence or like just random rocks falling on you, but it has no handles or usable intelligence. So that's exploration. Then you start modifying the environment a little bit to be more habitable for your robot or your machine. Let's call it a general term now. So the machine that's in a pure exploring environment, I think that can be considered unambiguously a robot since it has to carry all its intelligence within itself. Once it starts using tools and modifying the environment, it's starting to become less of a robot because some of the intelligence is now in the environment, and it's becoming more of like an appliance like thing. Take it further down the spectrum, if it's an extremely built environment and it's in the process of building it, it's now a construction kind of machine where the environment is already hospitable. So it's like maybe been leveled and there's like raw materials, regular shaped bricks and stuff. So if a machine is picking up building blocks that are well behaved and whose rules are clear, and it's like building up, say, buildings and other structures, is it a construction machine or a robot? I think on sort of a fuzzy scale, it's somewhere halfway in between. And once you get to like a completely sort of like built environment where almost all the intelligence is in the environment, like say the inside of a factory where there's a lot of jigs and fixtures and conveyors and other things doing a lot of the thinking for the task. And maybe the robot at this point is maybe just um, it might still have a little bit of intelligence. Like think of a factory pick and place robot, right? It's a camera. It identifies whether like tomatoes are good or bad. It picks up and throws away the bad tomatoes and lets the good tomatoes continue, right?
Yeah.
All this a pick and place robot, but at this point it's like basically image recognition in a loop with something close to a machine, because you can even imagine doing this without a robot style manipulator arm machine. You can think of it as like, a 19th century type mechanism with just a piston that just pushes the bad tomatoes out, right? Lots of
Yeah.
automation machines look like that. They don't have many degrees of freedom. They just have enough to do the task. So I think we had this discussion almost 2 years ago. The other discussion I remember having is there's another sense in which another kind of environment is a wilderness, which is basically human adapted environment. So this is Asimov's thesis for why humanoid robots are good, which is the environment is already built up with a lot of affordances for humans. So if you can program or build a robot that can operate like humans, you can reuse all that infrastructure. So I think I was brainstorming this in relation to what would a kitchen robot look like, where cabinets or counters are at a particular height. There are some vertical surfaces you can climb. Maybe you can put like a ladder or a groove, that kind of thing. I don't know what this is. This is a different kind of robot. And the thing is, so it's a different kind of wilderness, and it's a more structured environment, but it's still an alien type of grammar. It's not like learning the laws of nature in like a wild Martian environment. It's more like learning the human API that humans have created in a kitchen and then sort of like acting like that. And one of the effective ways to do that is to be in a humanoid form factor yourself, but that's not necessary, right? I think I gave the example of my cats jumping around, and they've kind of colonized the human apartment, but they actually use many of the affordances of a human apartment better than humans, because they can like crawl under the sofa, jump up, and things like that. So it's not as restrictive as it seems. So that's, I guess, two dimensions. One is wild to completely civilized. So that's where is the intelligence distributed, and how hostile it is. So like a wild environment is somewhere between hostile to neutral. So on Earth, if there are like, I don't know if you guys saw the video of the cat in Ukraine swatting at a drone and bringing it down. So there's hostile intelligence in the environment, but neutral. Neutral is like a rock falling. So, but still, there's intelligence, but it's somewhere between hostile and neutral. And apartment is something like there is intelligence, but it's neither hostile nor neutral. It simply hasn't considered other than human intelligences. And if those intelligences learn to navigate, it might still be friendly. But anyway, so I'll TLDR this recollection of two meetings into, I guess, one candidate definition for what makes a thing a robot, which would be something like it is a robot if the environment contains hostile to neutral intelligence or intelligence that is alien, and you kind of have to learn to adapt to basically environmental intelligence that was not designed for you. Okay, that's a good definition. A robot is a machine that has to adapt to environmental intelligence that was not designed for it. So that's one thought.
It's like if you have an unbound and uncontrolled environment, then it's mostly a robot. Otherwise, it's automation.
Well, I really liked how several of what the examples you talked about were actually about intelligence and not about robots.
Yeah.
Okay, and let's put aside the nature versus a competitor for a second. When you talk about the robot needing to deal, so what you're saying is that you're looking at robotics as where the intelligence is embodied. Is it more autonomous or less autonomous? But one of those robots in a factory painting cars has no intelligence. Okay, it has a teeny bit of adaptability, if the piece is a little bit different, but everything else is exact motions that it was taught. And the reason why it's called robotics and the reason why it's difficult, and it is difficult, otherwise we would have had it in the 18th century, is because you have to have precise control and calculations of multiple joints and things moving in space and so on. So I think today, if somebody built a robotic arm, which does, precise movements, we'd understand that it's a robot, but we wouldn't think it's an interesting robot. Well, if we make a little fly, which does exactly the same movement, we'd say, oh, well, wow, there's air current and it's difficult to control your position and putting it all in a small package and so on. So
But
we've talked in the past about how what makes robotics difficult is that you have not one big problem to solve, but you have multiple, at least technically complex problems that you have to solve simultaneously. And they all involve movement and possibly involve um, unexpected environment.
There's also an element of programmable adaptability, is how I would put it. So I don't think the key is like the need for precise and complex calculations of movements, because you actually had that in like the later era of mechanical clocks, and orreries are an example I'm thinking about a lot right now, because the book I just read, Thing Knowledge by what's his name, Davis, um, it talks about the history of like how people started like basically putting knowledge in things, and the knowledge was embodied by things. And one of the first examples he analyzes is an orrery. So an orrery is basically a model of the solar system, very complicated gearing that basically physically embodies all the movements of the planets and orbits and stuff like that, right? So precise calculations were happening in a mechanically embodied form. Uh, but I think where you start to get robotics is actually the same place you start to get computers, which is programmability. So what makes a industrial robot a robot as opposed to like, a CNC machine tool, is that even though both can be programmed with G code, they use the same programming model. The programming model can actually do a lot more with a 6 degree of freedom mechanical arm than it can with a CNC lathe, for example. And by that I mean, it doesn't matter how clever you are at writing G code. A lathe can fundamentally do only three things: it can rotate a spindle, it can move a bit in and out, and it can move the bit in parallel to the joint. So which means all it can do is produce some sort of like turned shape, right, with a circular cross section. Same thing with a milling machine. A milling machine is basically 2 degrees of freedom with one vertical degree of the tool itself, which means you can do like flat forms with built up contours, kind of like a 3D printer, but you can't do more. But the minute you do a proper 6 degree of freedom arm, the programming hasn't evolved. Keep in mind, you're not like suddenly replacing the programming language with classical planning or machine deep learning or anything. It's still G code. It's still very basic stuff, the same kind of stuff you see in 3D printing. But suddenly it can do a lot more because the mechanics have become unconstrained and more expressive.
but for me, like if you're still programming it in a like a defined way, the arm is still automation. So, for example, if there is a lathe machine and then the arm is just picking up the product and then placing it into a box without like, let's say, then it's just automation. But then once it's able to recognize there is a human inside and it can work with the human, and then it starts becoming a robot. It's like there is some sort of live play needed for it to become a robot.
So yeah, let's flesh out the spectrum then. Okay, so we just talked
Two
about
by
the
two, it's not a spectrum.
no, I think right now we're still on a spectrum. We need another dimension, but that can come later. But okay, so you have like a if you've ever worked the lathe, mechanical lathe, you're like set the speed of the spindle, and then you slowly move the bit with one hand, and then with the other hand you turn the crank to move it along, right? And you are the feedback loop. The human is the feedback loop in the sense that if the bit goes too far, you're the one who detects that and pulls it back. So one immediate step is the sort of like ladder of increasing complexity feedback. So the most simple kinds of feedback that you can have in such machines is basically limit switches, right? Some degree of freedom goes too far to a spectrum, it triggers like a mechanical switch and stops the motor. So it's extremely dumb feedback loop. That's like 0-1 type feedback loop. it's like, all right, it's I don't know, maybe some axis is moving at a very steady rate. It hits a limit switch, the motor turns off or motor reverses. So it can do maybe an oscillation motion if the motor reverses, right? Then you can say, all right, can we do a little bit more? Can we, instead of a 0-1 sensor, can we make it a continuous sensor? Can we couple two sensor measurements? So yeah, you can slowly build up with more and more sophisticated feedback. And I think the endpoint, maybe not endpoint, but the current point that we have converged to is the most generic feedback sensor we know of, which is the camera, which is, it gives you an image of a very complex scene, and then you can analyze it in very general ways and do other things. But it's still, the basic principle is spectrum from a limit switch 0-1 operation all the way to camera, which produces like a frame or a sequence of frames, and then you decide something based on that.
Well, is it a feedback or the intelligence which allows you to make use of the feedback that you're really looking at?
The intelligence can also be very simple, right? You don't need a full human equivalent brain. So the simplest kind of feedback loop is just on
Right,
off, right?
right.
The second intelligence level is
But that's
proportional.
not a robot.
Yeah, but on off, PD controller, PID controller, LQR regulator with a Kalman filter, right? You can slowly build it up. And at some point, my point here is there's no qualitative leap. It's kind of like a smooth gradient. You can just keep adding more and more sophistication until at some point it starts being able to do things similar to a human.
Will you agree that a Waymo cab is less of a robot than Spot the dog?
Yes, for similar reasoning as my comparison of CNC lathe versus a 6 degree of freedom arm, right? Because
Right.
the Waymo car is wheeled, it's adapted to run on roads, its turning is like very limited, it does very few things, whereas the dog can run all over, climb, do backflips. So yeah, it's more mechanically expressive.
So,
So
so these are your two dimensions. One is the mechanics, and there seem to be two kinds of mechanics. One has to do with the quality of feedbacks that you get, and the other one has to do with a range of actions that you have. And the other dimension has to do with intelligence. I don't know if it has to be embodied or can be remote, which is adaptable.
yeah.
But and then the most interesting intelligence is the one that deals with opponents in the world. Okay, so you can have a dog, a wheeled robot, which has to deal with the fact that we live in a human world, and then you can have something more sophisticated, like a car, which has to deal with the fact that other cars are dynamic. It's not just the world; the whole dynamics is problematic. And then you can have an actual device which has to deal with opponents which interfere with you intentionally. You move, they move. Okay, so at least from the YouTube videos we see, the autonomous cars don't know how to deal with that. Okay, they don't know how to avoid getting caught in all of these traps where you make them go around in a circle
Yeah.
or whatever. So I have to ask, what is the interaction between these two dimensions of complexity? Okay, so if we think about it as a 2 by 2, simple intelligence, simple mechanical, okay, that's clear. Simple mechanical and high intelligence, which, it compensates for the mechanical and vice versa. But what about the high mechanical, high intelligence? How do these two work together and not just, compensate for the.
Uh, okay, I think this still fits within the paradigm if you add
Mhm,
computational complexity and speed of response to the mix. And here's what I mean by that.
mhm,
You've got like more and more complex feedback loops, right? But feedback loops in the control theory sense are all finite time like low computational complexity responses. At most, it might be doing like, a polynomial calculation or like inverting a matrix or something like that, where the key property is it can be done in basically a predictable bounded time. So you can like determine the properties of the loop. And this is, by the way, in the structure of the brain as well. So if you look at how neuroscientists partition the brain, they distinguish between brainstem responses, which are closed loop, and then the cerebellum responses, which are kind of like adaptive closed loop, but can have like somewhat longer delays, to what they call open loop responses, which is sometimes you run into a problem that you basically have to sit and think, and you have no idea how long it'll take you to figure out an answer. And you might still need to continue doing something in that period, which in the Waymo car would be, I don't know what to do, but I have to do something. So I keep going in circles until I figure it out. So lifelock, deadlock, or basically, and I think the boundary has something to do with uh, P versus NP, but in a more practical sense. It's not that you start getting a robot when you have NP complete problems. It's more like once you are in NP complete type problems, you can't solve them exactly in finite time. So you start doing approximations and heuristics, and that puts you in like a very different behavioral mode, because now you're not in guaranteed behavioral regimes. So that's one point I wanted to make, which is the transition between what you're calling low and high intelligence is kind of, I think, equivalent to P and NP, or closed loop and open loop in the finite time response sense. But the other point I think you brought up is this match between what I would put as mechanical expressivity. So, 6 degree of freedom robot arm versus car that runs on tracks or something. That expressivity. And then you include the overall environment as well, an environment which does nothing but just sits there, versus an environment that is also dynamic and moving, versus an environment that's like active and intelligently trying to outwit you, right? So there's a spectrum of how the environment is intelligent. I think the way to think about this is there's this principle I may have cited before. It's called Ashby's principle of requisite variety, which says what is it? Something called a good regulator theorem, I think it's called. It basically says the controller has to be as complex as the thing it's trying to control. So this is sort of the informal way of putting it. So if the thing you're trying to control is a single degree of freedom mechanical object with like, Newton's law, then the controller can also be a second order controller, but, which basically reflects and reproduces Newton's law. But if the thing you're trying to control is like, I don't know, complex waving piece of cloth, it has to be like a full partial differential equation of the waving cloth. If the thing you're trying to control includes an environment with like an adversary that may be coming up with very clever strategies against you, which are basically like, NP or Turing equivalent sort of like programs it's running, then you have to be a Turing equivalent computer as well. So I think that's kind of the limit that we understand technically now, which is if your environment is acting in a Turing complete way against you, you have to act in a Turing complete way to respond to it, right? Which may include NP complete problems that you have to solve along the way.
So everything that you just said is just as applicable to social institutions. Okay. I mean, usually social institutions are very expressive, but not always. Sometimes they can only do one thing. And but you haven't exactly answered my question. Or maybe I'm just going to change my question a little bit. As an engineer, we try to minimize. So if I can solve the problem using a more expressive mechanics, let's call it, I'm going to try to get away with a less expressive intelligence, or vice versa. And the question
is, your friend who said that if you need a robot, you're a bad engineer. I think the assumption they're sneaking into the question is you have a well-defined close-ended problem, and The way I
Hmm.
would define a close-ended problem is, can you close off the boundary of the domain you have to operate in and then start modifying the environment itself? Because if you say all I'm doing is I'm trying to solve the problem of separating good and bad tomatoes that are in one
Right.
container and putting into another, close-ended fixed problem, the first thought is not to design a robot. The first thought is to like design a room and a conveyor belt and like create a completely closed and controlled environment where yes, you can be extremely dumb. Whereas I think with robotics, you don't start with such close-ended objectives. And also I think even if you do have a close-ended objective, like find water on Mars, uh, either the constraints of the problem prevent you from closing or reshaping the domain too much, or as a matter of principle you don't want to solve that problem that way because you're only trying to solve that first problem to create general capabilities to solve other problems, right? If finding water on Mars is your only problem, then maybe you can have like a very dedicated specialist water finding mapping machine. But if you want to say that, all right, I want to send only one machine to Mars and its first mission is to find water, but then the next mission will be to, and process the minerals and like build a building out of like bricks it creates itself. Now suddenly you're looking at a universe of like future missions that become an much larger and ambiguous target space, right? And then you would say, no, I don't want to design the simplest possible known robot machine.
Well,
I want to design a robot.
let's take exactly what you said and look at our trajectory of technology in the last, I don't know, about 30 years. And 30 years ago, if I had to build, I actually like the potato chip machine better. When I first thought of it, I was blown out of my mind. You cut a potato. If you have a black spot, you pass it back to the beginning of the machine. And if you don't have a black spot, you push it off into the packing. And then you cut it in half again. And if you have a black spot, and okay, and it's very, very, very clever. But what it really means is that a human intelligence did two things. It looked at the problem space and constrained it in a certain way, and it looked at the problem space and found a simple solution which didn't need adaptability. So that's how we used to solve problems once. We used to think a lot about it. Let's go forward to today. I have a problem in something that I don't know how to do it. Let's say some software. I have ChatGPT tell me how to do it, and ChatGPT uses the most complex libraries it can find to put together the software. And maybe even the software uses AI. I always say that using machine learning to solve a problem is, instead of having a PhD research it and then you know what's happening, the AI just finds correlations and you don't know what's happening, but it works just as well, arguably. So the way we solve problems today that require analysis and so on, to the extent possible, we just throw as much AI at it as we can. What we don't usually do is throw as much mechanical expressiveness as we can. But we've talked not that long ago about um, robotic modularity and standard parts. And as time goes on, we're actually more and more capable of throwing mechanical expressiveness at problems as well. So we're getting robots, so to speak, which are mechanically expressive and intelligent, but maybe we don't need either. It's just us that are, not so good at what we're doing. So we take a robot, any robot, we put an NVIDIA um, processor on it, we put an Oak automated vision system on it, We connected the most sophisticated algorithms for planning, and wow, now we have a little Roomba that can go around and pick up socks and wash the floor.
I think somewhere in there we snuck in either or dichotomy between simple solutions for well-defined problems versus kind of like general capabilities that I don't think is actually necessary. Like if you think about the Curiosity and Perseverance Mars rovers, there's one problem that they solve with extremely dumb mechanical intelligence within what is otherwise an extremely complex like robotic thing with a lot of other intelligence going on, namely the differential bar, right? It's a very clever mechanism. All it is bar that pivots in the middle, and when one side goes up it pushes the other side down. That's all it is. And I was very impressed with how clever it was, right? It's even simpler than the differentials that you find in Earth transmissions of Earth cars.
Right.
It's much simpler. So, but it's so the way I would think of that is in an intelligent problem-solving context, what look like simple, dumb point solutions actually become part of the language you use for more general capabilities. So I would say that one good answer to your a friend who says if you need a robot to solve a problem, you're a bad engineer, is to like take it one level above and say, well, okay, what does he think is a good engineer? Well, a good engineer presumably comes up with the simplest solution that does the job. Well, you come up with all the solutions and you put them into a big database of CAD models, and then you train an AI on that, and then it starts to like put that together for things it needs to do, right? So it might be a
Right.
very flexible looking dog robot that does acrobatics, but its leg may use like a very simple solution to a simple problem that comes from like a 14th century clock, right? So I don't think there's a either or dichotomy here. But yeah, that's actually a good segue for your second question, since we're about halfway, which is, all right, what makes it an AI robot? And I think you just gave the first answer to the question, which is the tr- gradual, again, transition between a regular robot based on everything we've talked about now and an AI robot is it might be inscrutability. It's like, all right, now we are into ways of like designing and fabricating robots where when the thing is starting to when you turn it on, yes, it solves the problems you had originally, but you don't know how it's doing it. It does weird shit. And sometimes you can, after the fact, you can deconstruct the behavior and say, oh, yeah, that's how it's solving the problem. But other times it may be solving the problems in ways you don't know or you don't understand at all.
Hmm.
So inscrutability is the leap between regular and AI robot.
But do you actually need that inscrutability? It's inscrutable because you're lazy, not because the problem requires it.
It might not be lazy. It might just have discovered a solution in like a very high dimensional space that you simply can't intuitively understand, right? Um,
I don't mean that the robot will not, the intelligence will not do exactly what you said, but I'm saying if I look at a robot and it has a big NVIDIA things there and and 20 gigabytes of RAM and so on, and 15 sensors and actuators, sounds a bit like a car. But if I find a robot that does that, it doesn't mean that it's actually necessary in order to solve the problem as defined. Okay, we can imagine um, the next generation of AI takes the Waymo problem, we'll call it, and gives us a simpler solution that has fewer mechanical components and less intelligence, which maybe makes it more robust. Okay, we can imagine that happening. And what I'm saying is that a lot of problems today, which are using, you know, AI and complex mechanics, in 20 years, so to speak, they'll do what you just said about suspension in the Mars rover. That we can make a simple suspension which does what it needs to do, and because it's simple, it's actually more suitable for the problem. So I guess I'm perhaps wondering, and you said before about um, how clever is the world? If the world attacks you with Turing complete, I don't know, interference, then you need to be Turing complete. I don't think it's a good measure because Turing complete is just the first step. It's the beginning, but there is a way of saying, do I really need a smart robot?
I think you're repeatedly returning to the idea of a defined problem, which may be the problem. Maybe the thing we need to discuss is what's a spectrum of motivated behavior ranging from closed end problem solving all the way to like the kinds of things humans do, right? Sometimes we solve problems, which is like, how do I earn money or how do I make a cup of tea? But other times you're just depressed and sitting back and thinking, what the hell am I doing with my life? That's the other end of
Depressed robots?
huh?
What is the name of the depressed robot in Hitchhiker's
Marvin,
Guide?
yeah, Marvin
Yeah.
and Hitchhiker's Guide, right? So yeah, maybe that might be a good example to begin with. Uh, how would you design a robot that's so again like take your friend's idea of like um, he has a very simple problem in mind and therefore a robot means you're a bad engineer. Keep broadening it, not just one problem but a range of problems, not just a range of problem but a high dimensional, high variety range of problems. And at some point you get to what I once called human equivalent problems, which is you kind of have to be live a full human life to be faced with such problems. So an example is like making a living. So I define that as a human complete problem in the sense that every challenge of life kind of gets rolled up into how to make a living. Like what's your philosophy? Do you believe in honesty? All these other things we think about get rolled up into the problem of how to make a living, and therefore it's a human complete problem. It's equal to the problem of life itself. So I think you
Hmm.
can keep expanding the domain of a robot's problems until it becomes like human complete. So what's the simplest? So this is like a different version of the Turing test. What's the simplest problem you can give to a robot, at which point it'll basically be a human complete entity that can suffer things like depression and angst? Like take your Waymo car, right? It's already mechanically and intelligence wise it's got enough power. But if you told that Waymo car, or there's no longer a corporation that owns you and like handles the money side, you're now a free agent car taxi, and you have to go around figuring out how to like earn enough money to maintain yourself and buy gas and stuff like that. So that's an interesting problem, right? Because now suddenly you've given it a human type problem that I suspect will produce the equivalent of like depression and things like that. It's like, all right, I haven't gotten a single customer for 3 days and my gasoline is running
He's
very
going
low.
down.
I'm sitting here and or my battery is discharging. I'm about to die. I'm depressed, right? So
This is similar to the difference between. I had asked on Wobcast, like, what is the difference between AI agent and a bot, like a
mhm.
Twitter bot, and then Na had a good definition. Like, agents have both tempo and interruptions, but bots either have one.
Huh.
So, so that is an interesting
Can
way to
you
think
can you
about it.
repeat
Like,
that? Can you repeat
so
that?
basically, I asked like, what is the difference between a bot and an agent, and now replied,
Right.
agents have both tempo and interruptions. Bots have one, not both. So either like you have a regular interval reaction mechanism in the bot, or like a particular type of re- reaction or interruption. So if you interact in a, if you interrupt the bot in a certain way, then it reacts. But but you don't do both in bots.
So
But
basically a cron job versus an API call, for example, right?
API calls also have a defined interaction mechanism, right? But like with
So
AI
internal.
agents, yeah. So basically, yeah, interruptions is like basically you have a defined way of interacting with the robot. But with LLMs, when you inject LLMs into the bot paradigm, you basically have like you can change both of them at the same time. I think that is a good way to like think about robots too. So
This reminds me of another definition I heard long ago between objects and agents. So this was back when they were doing trying to do agent oriented programming as a
Hmm.
evolution of object oriented programming. And some I forget who came up with the definition, but something like objects do it for free, but agents do it for money. And by this, they're making the comparison at the
Yeah,
level
yeah.
of an object has methods and properties, and you can invoke a method on it, but you invoke a method, it'll do it. It's not going to say no. Whereas an agent, the definition is you invoke a method, but it'll say, all right, now show me the money, right? Um, and this is, I think, actually, it might be a very similar point because injecting economic thinking and market thinking into the behavior of a software object is very similar to injecting an LLM into it. Both create a kind of unpredictability that allows richer behavior. But I'll have to think more about the.
or more dynamic interaction.
Yeah, but the fixed tempo versus interrupt response or both, and then that's worth thinking about. Now always comes up with very weird angles on everything. I don't understand half his responses on what. What
But
is
yeah, like it took me some time to understand, but it's like a good way to think about it.
but I do think inscrutability has some role to play because yes, even though the solution to a particular problem may over time become more scrutable and be replaced by a simpler solution, the property of being able to come up with inscrutable solutions uh, is kind of interesting. And in a way, humans think like that too, right? Like alchemy before chemistry. So alchemy was like a bunch of superstitions and mysterious magical thinking, but a lot of it worked. They came up with formulas that worked. They came up with some principles that kind of made sense. It was just all messy and illegible, but then somebody cleaned it up, and chemistry is like a more legible and rationalized form of alchemy. So the inscrutability is partly about okay, let me summarize that as inscrutability can partly be a superstitious stage of knowledge, or it can be sort of like higher order intelligence that we may not be able to understand. We can't visualize in 4 dimensions, and maybe in some sense some machines can. There's a Richard Hamming quote about this, maybe computers can think thoughts humans can't think. I forget the exact details of the quote.
No, it shows that they can, but that's the difference between existing inscrutability and necessary inscrutability.
That's a good term to unpack further. Is there any such thing as necessary inscrutability, which even if it gets simplified by other AIs, is fundamentally always going to be beyond humans? And
But the answer is yes. In other words, if we go from the world of driving that we have today, and a Waymo appears with road rage, okay, a random mutation in the software, all the other Waymos are going to have to learn how to deal with road rage. And since road rage is being applied by an intelligent system, you have to be as intelligent as it.
mm-hmm.
And we already agreed, so to speak, that even the Waymo car, a lot of what it's doing is inscrutable. There's so much work on AI explainability because it's really difficult. So we should be expecting, if that happens, for the other cars to have to be inscrutable, because they have to be able to do and think complicated thoughts and plans to deal. It's like an arms race with the evil taxis.
Yeah.
So even if in our world we don't want to have it, we're going to have it, and I think we're used to it. We have experts, in every field, hopefully, and a lot of these experts are opaque or inscrutable to other experts or to normal people.
So this is a version of the principal agent problem with added dimension of the principal cannot acquire the knowledge of the agent. So this is agent in
Yeah.
the economic sense, right? So
Yes.
if a doctor tells me some obscure diagnosis and says I must take this medicine, in principle, if I spend 5 years, I could get a medical degree myself and
Absolutely.
like check, right? But
But you'll be dead in a week. No, you can't
well,
do it. No, you can't do it.
yeah,
You can't do it.
exactly. So bounded rationality comes in there, where in this case the bound is the mortality bound. In other cases the bound may be the IQ bound, like maybe I'm not smart enough to get a medical degree. In other
Yeah.
cases it could be that no human is smart enough. Like this is already true of like chess and Go, right? No human is currently smart enough to actually beat computers at chess and Go, which means that fundamentally they've discovered solutions to any position in the games which are inscrutable to us. Like maybe particular lines of play can be simplified and humans can learn to play that opening or that type of game. But in general, they've solved those games in a way that's out of reach for us.
Yeah. Well, that article that you sent me about weird behaviors in artificial life, basically,
Mhm.
that's exactly what it's saying. Okay, it's saying we found all these weird behaviors. Some of them we can explain or justify, but some of them, surprise us.
Yeah.
Not surprise us that the machine was so smart, but surprise us that that solution actually exists.
And this is one of the kinds of things that makes me like really skeptical of the super intelligence or AGI type crowd, because you can kind of find examples like this with um, biological animals we think are dumber than us. Like at some level, cats and snakes and even trees can do weird stuff that fundamentally I can't model or replicate or in
Right.
even a metaphoric form reproduce, right? So there's something very, I don't know, situated about intelligence in this sense. Anyway, so I think, have we reached any conclusions? We have 2 minutes to summarize all this in one brilliant line.
Well, I'm expecting a two by two. And then when you look deeper in, you get another two by two on the necessary inscrutability versus uh, um, what should I call it? Um, nastiness of the world.
I think we have the basic template 2 by 2 of from your questions itself. Is a robot, is not a robot, is an AI, is not an AI, right? So a hammer is not a robot and is not an intelligence.
We
And
agree.
other opposite is also kind of there, like um, acrobatic dog that does the acrobatic dog equivalent of like chess or Go stuff is probably both an AI and a robot, right?
Right.
And those other two quadrants may or may not be interesting.
No, I think they are interesting because most of the world doesn't require AI robots. Most of the world can be satisfied with unexpressive mechanics, but which is driven by intelligence. In other words, a person with a hammer thinks everything is a nail. That's the only thing they know how to do. But if it's a person, they can do quite a bit. And on the other side, you have a very sophisticated machine, but the software, so to speak, is really simple. And because it's really simple, it's reliable and can win, let's call it.
This reminds me of another thing. Have you guys read the Ian M. Banks novel Player of Games? So I think it's the second novel in the series.
I think I did. Let's say it's difficult to remember.
So for Anuraj's benefit, this whole science fiction series is set in a world where galaxy where the galaxy is run by super intelligent spaceships, basically. That's how Elon Musk's uh,
No, I didn't read it.
landing ship names come from.
Okay.
Is right.
The drone
Yeah,
land
yeah.
landing ship.
Not enough gravitas, that kind of thing. So these super intelligent ships give themselves names, but this particular plot, I'll give it'll be a spoiler. But the super intelligent ships kind of want to basically make the whole galaxy more humane, better place, and they're against oppression, etc., everywhere. And they find a planet where it's basically an evil dictatorship, but the entire society is run by a very complicated game, kind of like, hyper chess or Go or something like that. So if you can do well in the game and win, you'll be the ruler and you can oppress everybody else. So that's the premise. And the super intelligent ships want to take down this culture and replace it with a better culture. So they recruit a guy who's a good games player from some other random human planet. So he's not particularly good. But then on the voyage to the target planet, they basically train him in the game that the alien planet plays.
Hmm.
And they train him very, very effectively so that when he goes and participates in the tournament, everybody's surprised. But even though he's never been there and it's the first time he's playing the game, he beats them all and he becomes the ruler of the planet. And, that's a spoiler, by the way. But I remember after reading that, thinking that the AIs injected more inscrutable intelligence into the guy's head than he himself was aware of. Like he didn't realize how good a player he'd become because he'd almost been like a virus. The
Yeah.
machines programmed him. He became their tool, right? So it's
Oh.
uh,
I, I, I just want to stop you for a second. Viruses for robots is something that we have not talked about, but we
yes.
definitely should.
This reminds me of I don't know if it's true or not. Somebody had trained a dog to throw stones or like bricks when somebody was at the gate. And he was, I don't know if it's true, but
Oh
I've
yeah,
seen.
yeah.
Yeah, yeah. I don't know. Somebody was fined or something, so the dog would throw bricks when somebody.
There's a whole movie with this kind of premise called the Doberman Gang. Have you guys watched it? So a bank robber trains a set of Doberman dogs to basically go rob a bank. So the complete heist plan is they're trained to do it and they're like trained to bite the guards, stuff like that. The plan goes horribly wrong, of course, but the dogs do manage to rob the bank and execute 70% of the plan before things go bad. And yeah, so that's another thing worth thinking about. Like maybe behavior can be more intelligent than sort of the last mile intelligence that thinks it's in charge, right?
Yeah.
So in a way, this is almost a religious idea. Like a higher intelligence may program you to do more intelligent things than you think you're doing, right? So that's
Yeah, that's a dimension we didn't explore when we talk about embodied intelligence. The true, I don't know, true, but an important sign of intelligence is making other agents do what you need.
and then they think they did it themselves. I think this is a Sun Tzu quote in Art of War, which is when, or maybe it's Lao Tzu. It's something like when the wise king does what he does, the people say, "Hey, we did it ourselves." Something like that. The exact quote is a lot more poetic, but you get the idea.
Yeah,
Sadly, few
but but
politicians these days follow.
but maybe you're happy to do it. You don't do it unaware. You're happy to do it
Yeah.
because you think there's an alignment of interest, and there is an alignment of interest. That's called, having a job. You get paid, and shareholders make much more than you do.
And I think a lot of free market type people would say that the invisible hand is exactly this kind of argument. The market effectively makes us all much smarter in our behavior, even though we are all acting like we are in much simpler systems, right? So the market overall is more intelligent. So yeah, there's a lot to unpack here. Anyway,
Yeah,
we're calling it time.
yeah, yeah. 5 minutes past. So
All right. Good discussion.
see you next week.